In this video, we're going to take a look at a new concept, and it's called the law of sines. So let's jump right in and take a look at the law of sines. To kind of help us understand what's going to happen here, I want you to take a look at this picture and this question. It says, what is the relationship between the sine ratio of each angle in this triangle and the side lengths of the triangle? Now, as of right now, when you see something about sine ratio, you're probably thinking about SOHCAHTOA, right? Let me write out SOHCAHTOA here. We learned before about SOHCAHTOA and the fact that the sine ratio is equal to the opposite leg of the angle divided by the hypotenuse of the triangle. And the fact that that uses the word hypotenuse tells us that this version of sine, this definition of sine, only applies when we're dealing with a right triangle. And if we look at the picture over here, this does not appear to be a right triangle. Angle A looks like it's kind of close to a 90-degree angle, but it's not marked as a 90-degree angle, so we're not going to be able to say that it is. So this triangle right here does not appear to be a right triangle, which means that our previous definition of sine is not going to really apply here, and so it might initially seem that we can't even answer this question, that there's no, or maybe we would just say that there's no relationship between the sine of A and the side lengths of this triangle, right? It would not necessarily be opposite over hypotenuse because we don't have a hypotenuse in this triangle because it's not a right triangle. But in fact, if we take a look at this and we add a segment to this picture, we are going to be able to see a relationship between angle A and the sine of angle A, and we'll find out it's going to be segment BC, or the length of that segment A, and a relationship between B, the sine of angle B, and this side over here, and the sine of angle C and this side over here. So let me just show you how this is all going to work out. What I'm going to first do is I'm going to drop in an altitude from angle A straight down to the opposite side. Now I know that altitudes go from the vertex of an angle, or vertex of a triangle, sorry, and go across to the opposite side and makes a 90-degree angle. In doing that, I've just created two right triangles in my picture where there wasn't any right triangles before. And I'm going to look at angle B, all right? And I'm going to label, first of all, I'm going to label that altitude as H, standing for the height of this triangle. Now, what I can say about sine of angle B is that it would be H over C, because now if I'm looking at, let me write that out just so we can kind of see it. I'm going to write that the sine of angle B would be equal to H over C. And that's because now I'm not looking at the triangle ABC, I'm looking at this smaller right triangle here. And since it is a right triangle, I can use this SOHCAHTOA definition for sine. And I'm going to say the sine of angle B is H over C. I'm also going to look at angle C over here. I'm going to say that the sine of angle C would be H over B. So let me write that out. The sine of angle C would be H over B. And again, I'd be looking at this right triangle right here, because if there's a right angle here, I know there's going to be a right angle here. And I can use, again, that SOHCAHTOA definition to say that the sine of this angle would be the opposite leg, H, over the hypotenuse of this right triangle, which is B. So now I have sine B equals H over C, and sine C equals H over B. And what I'm going to notice is that these two relationships, these two equations, both have H in them. And I'm going to take each one now and I'm going to solve it for H. So that's going to give me that C times the sine of B equals H here, and B times the sine of C equals H for this equation. Again, I just cross multiply. The H got multiplied by the imaginary 1 that would be underneath the sine C here and would be underneath the sine B here. That's why it ended up all by itself. And then in this case, C got multiplied by sine B, and B got multiplied by sine C. So now I have these two equations, but now they're both equal to H, which means that I can take this part right here and this part right here and set them equal to each other. So let's do that. C times sine of B equals B times sine of C. And I did that because, again, both of these parts were equal to H, so they must both be equal to each other. Now lastly, I'm going to do a little bit of reorganization of this equation. I've turned these two separate equations into one equation down here. Right? I did that by solving each one for h and then putting the parts that are equal to h equal to each other. Now I'm just going to reorganize this a little bit. I'll show you what I'm going to do. I'm going to divide this side by b and this side by b, and that'll give me c times the sine of b over b equals the sine of c, because these two b's are going to cross out. Then I'm going to divide each side by c. And that will then give me that the sine of angle B divided by B, because these two c's will cancel out, equals the sine of angle C divided by C. And this relationship here is kind of what we were after from up here. We looked at angles B and C to start with, and through a little bit of some fancy math, I guess, adding a segment in here, adding this height segment, and then creating these two equations based on SOHCAHTOA for these two right triangles, and then doing some algebraic manipulation of those two equations, it all boiled down to this relationship here, that the sine of b over b equals the sine of c over c. If I had chosen to draw an altitude from b across to this side, then I would have been able to do the same thing with angles a and c, and I would have ended up with sine of c over c equals sine of a over a. Just doing the same kind of math I have here. So what that means is I can go ahead and attach onto this, this statement here, I can attach one that says that the sine of angle A over A is equal to these other two ratios. And this right here, this is what is going to be known as the law of sines. So let's jump to the next slide and talk a little bit more about this law of sines. So the official wording of the law of sines looks like this. It says for any triangle ABC, and the fact that it says for any triangle there, that's important. Okay, I'm going to come back to that in a second. For any triangle ABC with side lengths A, B, and C that are opposite angles A, B, and C respectively, what that means is that the side that has length A is across from angle A, the side that has length B is across from angle B, the side that has length C is across from angle C. So we can kind of see that over here. Angle A here, side length A here, angle B here, side length B here, angle C here, side length C here. So for any triangle, when we think about its angles and sides this way, the law of sines relates the sine of each angle to the length of the opposite side. So it shows a relationship between sine A and length A, sine B and length B, sine C and length C. And that relationship is shown here. It's basically three ratios that would all be equal, three fractions, where we put the sine of each angle in the numerators, sine A, sine B, sine C, and we put the lengths of the opposite sides from each angle in the denominators. So on the bottom of sine A is A, on the bottom of sine B is B, and on the bottom of sine C is C. So again, keep in mind that capital A, B, and C, those capital letters are the angle measures here. These lowercase letters are the length of the side that's across from that angle. So whatever angle A is here, maybe it's about 80 degrees. This side is however, this value A is however long that side is, right? So we can take this relationship and we can use that for something very specific. Notice, again, I said I was going to come back to this idea that it says for any triangle ABC. The fact that this works not just for right triangles, but for any triangle, a right triangle or an acute triangle or an obtuse triangle, an isosceles triangle, an equilateral triangle, any triangle you can think of will have this relationship. And what that means is we can use this law of sines idea. It can be used to find missing parts, missing side lengths or angle measures in a triangle. And I should say it doesn't always work. You have to have a certain set of circumstances has to be present for you to be able to use the law of sines. And we'll start looking at what those circumstances might be as we get into the example problems. But this is the reason why we want to know the law of sines, because we can be given a triangle where maybe we know two of the angles and one of the sides, and we could use the law of sines to find the missing sides and the missing angles. All right? Maybe we're given two side lengths and one angle. We can use the law of sines to find the missing angles and the missing side lengths. And that's something we couldn't do before, right? For any triangle, we wouldn't be able to do it. If it was a right triangle, we could have used SOHCAHTOA or the Pythagorean theorem perhaps. But if it wasn't a right triangle, before this we were kind of out of luck if we wanted to find some missing pieces of information. But now with the law of sines and another tool that we're going to learn in an upcoming video called the law of cosines, with those tools we can actually find missing side lengths, missing angle measures in just about any triangle, so long as we have some other information about that triangle.